400 feet above the Clinch River in eastern Tennessee, a steel cable stretched between two towers anchored into solid rock. Hanging from that cable, swinging over open air, was an 8-cubic-yard bucket filled with wet concrete, weighing close to 20 tons. One operator on the far side controlled everything. If the cable snapped, if the bucket released early, if the wind caught it wrong, there was nothing between that load and the men working on the dam forms below. Between 1933 and 1944, the Tennessee Valley Authority built 16 dams across the American South using this exact system. They poured more than 10 million cubic yards of concrete, moved entire mountains of crushed rock by conveyor belt, and displaced over 15,000 families from land their ancestors had farmed for 200 years. And then the United States government took the electricity those dams produced and used it to build the atomic bomb. This is the story of the machines that built the TVA dams, and it starts with a river that nobody in Washington could control. The Tennessee Valley, 1933. 3 million Americans lived in a 40,000 square mile stretch of the southeastern United States, and the poverty there was so deep it had become invisible to the rest of the country. The Tennessee River flooded almost every spring, washing away farms, roads, and entire communities that had been rebuilt from the last flood. Erosion had stripped the topsoil from hillsides that early settlers had logged bare a century earlier. Where dense hardwood forests once stood, there was now red clay gullying down into streams that turned brown after every rain. About 2% of rural families in the valley had access to electricity. The average annual income in the region sat around $100 a year, less than half the national average. And the national average during the Depression was already brutal enough to put millions of people out of work across the country. A farmer named Horace Higgins, interviewed for a government film about the valley, described the situation in terms that have been preserved in the National Archives. He said there was no point filling up the gullies because the first rain washed them away again. He said the land might have been good once, but it was bad land now. His words carried the weight of a generation that had given up. Senator George Norris, a Republican from Nebraska, had spent more than a decade fighting to put the federal government into the power business in the Tennessee Valley. He believed that private utility companies were charging rural Americans rates that kept them in darkness deliberately. 2 presidents vetoed his bills. Calvin Coolidge said no. Herbert Hoover said no. Franklin Roosevelt, inaugurated in March of 1933, said yes. On May 18, 1933, Roosevelt signed the Tennessee Valley Authority Act into law. It created something the country had never seen before: a single federal agency with the power to build dams, generate electricity, control floods, manufacture fertilizer, and redesign an entire region from the ground up. The scale of the ambition was matched only by the scale of the problem. Roosevelt appointed 3 directors who agreed on almost nothing except the first project. Arthur Ernest Morgan, a self-taught hydraulic engineer who had built the Miami Conservancy District flood control system in Ohio after the catastrophic Dayton flood of 1913, became chairman. He was an idealist who saw TVA as a chance to build model communities and reshape American rural life. Harcourt Morgan, no relation to Arthur, was the president of the University of Tennessee and handled the agricultural side of the operation. David Lilienthal, a young lawyer from Wisconsin with strong opinions about public power, took charge of electricity policy. The 3 men would eventually clash so badly that Roosevelt fired Arthur Morgan in 1938. But in 1933, all 3 agreed on one thing: build the dam on the Clinch River first. By October 1, 1933, construction had started about 20 miles northwest of Knoxville. The project already had a name: They called it Norris Dam, after the senator who had spent 12 years trying to make it happen. If you are enjoying this documentary, take a moment to like and subscribe. It helps us keep making these films about the machines that built America. The single most important piece of equipment at Norris Dam was not a bulldozer or a steam shovel. It was the overhead cableway. This was a system manufactured by the Lidgerwood Manufacturing Company of Brooklyn, New York, and it was the same technology that had been used to pour concrete at Hoover Dam 3 years earlier. The Lidgerwood Company had been building cableways for dam construction since the early 1900s, with installations at Roosevelt Dam, Elephant Butte Dam, Arrow Rock Dam, and Blewett Falls Dam. These installations spanned anywhere from 800 to over 1,400 feet, with capacities of 10 to 25 tons. Here is how the system worked at a TVA dam site. A stationary head tower stood anchored on one abutment of the dam. On the opposite abutment, a traveling tail tower was mounted on steel rails so it could move upstream and downstream along the length of the dam face. Between the two towers hung a main cable, and a carriage ran along that cable on wheels. From the carriage hung a steel bucket with a bottom dump gate. The entire assembly could reach any point across the dam face by combining the side-to-side motion of the traveling tower with the back-and-forth motion of the carriage along the cable. Concrete batch plants on the dam site mixed aggregate, sand, water, and Portland cement into wet concrete and loaded it into the bucket. The cableway operator, sitting in a control cab on one of the towers, then carried the loaded bucket out over the dam and lowered it to the correct position above the pour forms. When the bucket was in place, the operator released the bottom gate, and the concrete dropped into the forms below. Each pour went into a 5-foot thick lift. The dam was divided into interlocking blocks, and crews poured one block at a time, working across the face in a grid pattern. At Hoover Dam, where the main cableway stretched 1,580 feet between anchors with a usable span of 1,256 feet, crews needed up to 100 bucket loads to fill a single lift. TVA cableways were generally smaller in span, but identical in principle. The operator had no automation and no remote shutoff. He controlled the carriage position, the lowering speed, and the dump release using mechanical levers and friction brakes. A single miscalculation in wind speed, bucket weight, or release timing could drop 20 tons of wet concrete on a crew working the forms below. The system ran on cables, gravity, and one man's judgment. It was efficient, dangerous, and irreplaceable. Without it, there was no way to deliver concrete to the center of a dam, face hundreds of feet wide, and hundreds of feet above the river. Roland Wank, a Hungarian-born modernist architect, became the TVA's chief architect in 1933 and held the position through the entire 11-year program. When the Bureau of Reclamation delivered its original engineering plans for the Clinch River Dam, Wank looked at the design and rejected its appearance entirely. He felt the plans had an unimaginative and heavy appearance that lacked the simplicity that should characterize TVA work. He proposed a sculptural recasting of the dam's elements, replacing applied ornament with clean surfaces, carefully proportioned window openings, and the natural texture of concrete left visible by the formwork boards. Every TVA dam, built after Norris, followed Wank's architectural template. The streamlined modernist look that defines TVA infrastructure to this day came from one man's insistence that functional engineering could also be beautiful. Norris Dam rose to 265 feet, stretched 1,860 feet across the Clinch River, and used just over 1 million cubic yards of concrete. The base was 208 feet thick. 2 generators produced 50,000 kilowatts each. At peak, approximately 2,750 workers were on site at once, with over 5,000 different individuals cycling through the project across its 3-year construction period. The total cost, including land acquisition for the reservoir, came to approximately $36 million. Journalist Ernie Pyle visited Norris during construction in 1935, years before he became the most famous war correspondent in America. He wrote about looking over the edge of the unfinished dam, describing how he had to get down on his knees and elbows, take a death grip on steel reinforcing bars sticking out of the cement, and then peer over the edge just a little at a time. There was no guardrail. Pyle called the dam the foundation on which TVA planned to build its castle. The working conditions at Norris were better than anything the region had seen, and better than most dam projects of the era. Workers earned between 45 cents and $1 an hour, depending on skill level. TVA provided housing in the nearby construction camp and meals in the cafeteria. The agency also tackled a problem that had plagued the Tennessee Valley for generations: malaria. The mosquitoes that bred in standing water along the riverbanks and backwater pools had made the valley one of the regions with the highest malaria incidence in the eastern United States. Dr. E.L. Bishop, head of TVA's Health and Safety Division, developed a technique that became the global standard for reservoir malaria control. By deliberately fluctuating the water level behind the dam by at least 1 foot every 7 to 10 days during mosquito breeding season, Bishop's teams stranded mosquito larvae on exposed banks before the larvae could complete their aquatic development cycle. Wheeler Dam was actually redesigned during construction so that the height of its gates would allow exactly this kind of periodic fluctuation. The method worked so well that the World Health Organization later recommended it for dam projects across Africa and Southeast Asia. But building the dam was only half the work. Filling the reservoir behind it meant flooding 152,000 acres. That meant removing everything and everyone living on that land. Surveyors went door to door across Anderson, Campbell, and Union counties and told 2,841 families that they had to leave. The government would pay them for their property, though many families received compensation that amounted to a fraction of what the land was worth to them in terms of livelihood and generational attachment. Appraisers set values based on market rates in one of the poorest regions of the country, which meant the dollar amounts were often painfully small for land that families had worked for over a century. Some accepted willingly because they believed in the promise of electricity and flood control. Others had no choice. The government had the legal authority of eminent domain, and the water was coming whether they agreed or not. TVA relocated the 5,226 graves in the flood zone to higher ground, a process that took months and involved exhuming remains from family cemeteries that had been in use since the 1700s. Across the entire TVA program, over 14,000 graves would eventually be moved, and it would build them a new town. That town was called Norris. Arthur Morgan designed it as a planned community, a social experiment modeled on his earlier work at Antioch College in Ohio. It had 309 permanent houses, 8 dormitories, a cafeteria with 544 seats, a school for 400 students, a vocational building, a store, a gas station, and a recreation center. Norris was the most progressive company town in America in 1934. It was also racially segregated. Black families were not allowed to live there. TVA's hiring policy was ahead of its era in one specific and documented way. The agency paid identical wages to black and white workers: 45 cents an hour for unskilled labor, $1 an hour for skilled trades, regardless of race. A government report from 1934 confirmed this explicitly. At Hoover Dam, by comparison, fewer than 50 black workers were hired out of a total workforce exceeding 21,000 over the life of the project. TVA employed black workers at a rate matching their share of the local population. At Norris, that proportion was about 7%. but those workers were limited to reservoir clearing and road construction. They did not pour concrete on the dam structure itself, and they were barred from the homes and schools and cafeteria in the town that bore a senator's name. TV sold Norris to private owners in 1948. The experiment and its contradictions were over. While Norris established the template, the true scale of the TVA program revealed itself between 1934 and 1940 as construction crews expanded across the entire Tennessee Valley watershed. Wheeler Dam went up on the Tennessee River in northern Alabama. It was a run-of-river dam, meaning it sat lower than a storage dam like Norris, but it stretched much further across the valley. The finished structure measured over 6,300 feet from end to end, and at peak, the site employed 4,700 workers. Wheeler Dam displaced 840 families and required acquiring over 103,000 acres of land. The earth-moving crews at Wheeler used the standard contractor fleet of the 1930s, which meant Bucyrus Erie and Marion power shovels in the 1 to 3 cubic yard dipper range, crawler tractors for clearing and grading, and drag lines for moving loose material away from the dam foundation. These were cable-operated machines, working without hydraulics, powered by diesel engines or gasoline motors that required constant maintenance in the humid Tennessee Valley climate. Pickwick Landing. Dam followed in western Tennessee, stretching an enormous 7,715 feet across the valley floor and using 630,000 cubic yards of concrete. 407 graves were relocated at Pickwick alone, each one dug up by hand and transported to a new cemetery above the floodline. Hiwassee Dam in western North Carolina reached 307 feet, making it one of the tallest structures in the entire system, with 793,000 cubic yards of concrete. Chickamauga Dam near Chattanooga used 506,000 cubic yards. Like and subscribe if you are learning something new today. We put a lot of work into getting these details right, and your support keeps this channel going. Every one of these dams used the same Lidgerwood cableway and bottom dump bucket system that Norris had established. Everyone used the same 5-foot lift technique. Everyone hired thousands of Depression-era workers who showed up knowing nothing about concrete and learned on the job because there was no other choice. The cableway operators trained by watching other operators work, then took control of a system where a mistake meant 20 tons of concrete falling on the men below. There were no certification programs. There were no safety courses. A man learned the friction brakes and the dump lever in a matter of days, and then he was on his own with a loaded bucket, swinging 400 feet above a river. Every one of these dams also drowned another valley. Wheeler took over 103,000 acres and displaced 840 families. Pickwick took 63,700 acres and 506 families. The graves kept coming out of the ground throughout the entire program, with 407 relocated at Pickwick alone and hundreds more at each subsequent site. The process was the same everywhere. Surveyors arrived first, then the appraisers, then the letters, then the water. To prevent thermal cracking in these massive concrete structures, TVA engineers embedded networks of cooling pipes throughout each dam, circulating chilled water through the curing concrete to draw off the heat generated by the chemical reaction inside the hardening mass. This technique had been pioneered at Hoover Dam, where calculations showed the concrete would have taken over 100 years to cool on its own without intervention. At that rate, thermal stress would have cracked the dam from the inside before it ever held water. TVA adopted the same refrigerated pipe method and applied it systematically across the program. By early 1942, 12 TVA projects were under construction simultaneously, and the combined design and construction workforce reached 28,000 people, according to the United States Army Corps of Engineers. It was the largest dam building operation in history, and it was about to accelerate even further. Because the war had arrived, and the Tennessee Valley was about to become the most strategically important piece of real estate in America. Cherokee Dam on the Holston River was authorized on July 1, 1940. Crews broke ground the very next morning, before the paperwork had even reached all the regional offices. This was no longer Depression-era make work. This was military infrastructure, and the urgency showed in everything from the shift schedules to the supply chains. Workers poured concrete through the night under banks of floodlights that drew moths so thick the operators had to wipe their goggles between bucket loads. 16 months and 5 days later, on December 5, 1941, the last gates closed and water began filling the reservoir. That completion date fell one single day before the Japanese attack on Pearl Harbor. Cherokee used 686,000 cubic yards of concrete, nearly 1.5 million cubic yards of rock fill, and 2.5 million cubic yards of compacted earth. Cherokee recorded 15 worker fatalities during construction, with an injury rate of 13 per million man-hours, which was considered low for a project of that scale in that era. The dam was finished barely in time for what came next. The War Department needed electricity on an unprecedented scale. Aluminum production for military aircraft was consuming power across the country. But there was something else. Something that almost nobody inside TVA itself knew about. The federal government had already begun scouting locations for a facility that would use more electricity than any single industrial operation in human history. They needed a site near a major power grid, near a railroad, near a river for cooling water, and far enough inland to be safe from enemy bombers or submarine-launched attacks. The Tennessee Valley matched every requirement. Douglas Dam became the defining project of the wartime TVA. Senator Kenneth McKellar of Tennessee had blocked authorization for 2 months because the reservoir would flood 40 square miles of some of the best canning-grade farmland in the state. Pearl Harbor changed the political calculus overnight. Roosevelt signed the bill on January 30, 1942. Construction crews broke ground on February 2nd. Despite a 4-week delay caused by spring river flooding, the floodgates of Douglas Dam closed on February 19, 1943. That was 382 days after construction began. It was a world record for a major concrete dam. That record has never been broken. The logistics behind that speed were ruthless and brilliant. TVA engineers took the Cherokee Dam blueprints and reused them with almost no changes. They transferred the Cherokee workforce directly to the Douglas site. They moved the Cherokee construction equipment without pausing. A 30,000 kilowatt generator that had been ordered for Cherokee and manufactured ahead of schedule was redirected to Douglas before Cherokee even needed it. At peak, 6,220 men and women worked the Douglas Dam site around the clock in 3 continuous shifts. There was no downtime. The batch plants ran all night. The cableways swung concrete buckets through floodlights that turned the valley into artificial daylight. Steamfitter Patrick Marshall was one of 18 workers who did not miss a single day of work from the moment the project started until the day the dam was dedicated on March 1, 1943. His words were recorded for the ceremony. He said that he realized any day he was absent was a day given to the enemy. He said they were all united in the hope that the power they built would speed utter defeat to their enemies. 6,000 workers building a dam in 382 days, and one steamfitter who understood exactly what was at stake, even though he had no idea where the electricity was actually going. If you have watched this far, hit the like button and subscribe. It helps this channel reach more people who care about this kind of history. While Douglas set records for speed, Fontana Dam set records for everything else. The site sat in the remote mountains of western North Carolina, about 65 miles from Knoxville, near the border of Great Smoky Mountains National Park. There was exactly one road into the valley, and it was 1 lane wide with no shoulders. Before a single bucket of concrete could be poured, construction crews had to widen that road and build a 2-mile railroad spur just to transport heavy equipment to the river. The isolation was extreme. Workers arriving from other states described the site as the most inaccessible major construction project they had ever seen. The construction camp that grew around the Fontana site eventually held 19 dormitories, a 50-bed hospital, 400 permanent houses, 400 trailers, 2 racially segregated schools, a post office, and a cafeteria that served 6,000 hot meals and packed 2,000 sack lunches every single day in 1943. Workers came from all 48 states, and at peak the population of the Fontana camp rivaled many small Tennessee cities. The project manager, C.E. Blee, oversaw engineering operations, while site superintendent Fred Schlemmer handled daily operations, morale, and the camp's public address system that broadcast announcements and music across the valley. Fontana Dam stands 480 feet above its foundation. At the time of its construction, it was the 4th tallest dam in the world and the tallest east of the Rocky Mountains. That distinction still holds. The structure stretches 2,365 feet across the Little Tennessee River and contains 2,818,000 cubic yards of concrete. Roughly 5,000 workers built it, though some accounts put the number closer to 6,000 when reservoir clearing and camp staff are included. Wanda Presswood was a child when her father worked at Fontana. He operated one of the conveyor belt systems that carried 6 million tons of crushed rock from a riverside quarry across the river to the dam forms. In an interview preserved by Our State magazine, she described what she remembered seeing. She said all you saw was these levels being built, and night was day all the time. It was never dark over there. She called it the most beautiful sight. Bulldozers and cranes and conveyor belts running 24 hours a day, and the whole valley glowing against the Smoky Mountains like a city that had appeared out of nowhere. The concrete crews at Fontana set a national record that defined the pace of the entire project. They placed 11,419 cubic yards of concrete in a single 24-hour period. To put that in perspective, a standard concrete mixer truck carries about 10 cubic yards. Fontana's crews poured the equivalent of more than 1,000 fully loaded mixer trucks in one day, using cableways and buckets and batch plants running without pause from one midnight to the next. The pace was relentless, and the terrain was unforgiving. John Lee Patterson, another Fontana worker whose account survived through local history records, described a motorized shovel that careened off the brink of the rock quarry and tumbled 300 feet down the mountainside. He said it looked like a beer can mashed up when they started trying to salvage the wreckage. The operator, who rode the machine all the way to the bottom, survived with a broken arm. 14 other workers at Fontana did not survive. 14 men died during construction. 11 more were permanently disabled. 447 suffered injuries serious enough to be documented in TVA Industrial Hygiene Division records. The total project cost came to $70,420,688.48. 34.5 million man-hours of labor went into every cubic yard. The story of Fontana is also a story of what construction life looked like in wartime America. Many of the workers had never been more than 50 miles from the place they were born. They came to Fontana because the pay was good, because the draft board gave construction workers temporary deferments, And because there was a sense, even among those who did not know the real purpose of the electricity, that the work mattered. The camp ran its own newspaper. There were dances on Saturday nights. Workers played baseball on a field carved out of the mountainside. And every morning at 6 o'clock, the shift whistle blew, and 5,000 men walked toward a dam that grew taller with every pour, visible against the Smoky Mountains from miles away. If you have stayed with us this far into this story, take a second to like and subscribe. This kind of research takes real time, and your support is what makes it possible. Now we reach the part of this story that connects 16 concrete dams in Tennessee and North Carolina to the single most consequential weapon ever detonated. Every kilowatt of power that Fontana and Douglas and Cherokee produced was already spoken for before the generators came online. All of it was going to a fenced compound in the hills about 30 miles west of Knoxville, near the small town of Clinton. 75,000 people worked inside that compound. Nearly all of them had no idea what they were building. Security was so complete that workers in one building were forbidden from asking workers in another building what they were doing. The compound was officially designated the Clinton Engineer Works. The world would come to know it as Oak Ridge. TVA supplied up to 310,000 kilowatts of electricity to Oak Ridge through dedicated high-voltage transmission lines running from Norris Dam and Watts Bar Dam. 200,000 kilowatts went to the Y12 plant, where rows of massive electromagnetic separators called calutrons processed uranium ore into weapons-grade uranium-235. 80,000 kilowatts powered the K-25 gaseous diffusion plant. 23,000 kilowatts ran the township where those 75,000 workers lived. 6,000 went to the S-50 liquid thermal diffusion plant, and 1,000 powered the X-10 experimental graphite reactor. Oak Ridge was the single largest electricity customer in the United States during the war years. General Kenneth Nichols, the district engineer of the Manhattan Engineer District, later stated that Oak Ridge alone consumed 1/7 of all electricity produced in the country between 1943 and 1945. Later independent analysis revised that figure downward to approximately 1% of total national output, but the scale remains staggering either way. Oak Ridge consumed more electricity than many major American cities combined, and every watt of it flowed through transmission lines connected to the dams that TVA construction crews had been building since that first cableway went up over the Clinch River in 1933. David Lilienthal, one of the original 3 TVA directors appointed by Roosevelt, went on to become the first chairman of the United States Atomic Energy Commission in 1946. His career traced a direct line from dam construction to nuclear weapons policy. The Y12 plant's own archival history states plainly that one reason the Manhattan Project was located in East Tennessee was the proximity to the TVA dam system for electrical power, and that nobody at the time realized how enormous the demand for electricity would become as the atomic weapons program expanded. The dams that pulled the Tennessee Valley out of the Depression also powered the weapon that ended the war in the Pacific. By November 1944, when the last concrete at Fontana Dam was placed, the Tennessee Valley Authority had completed 16 hydroelectric dams in 11 years. The total concrete volume across the program exceeded 10 million cubic yards. That was more than twice the amount used to build Hoover Dam, the subject of another documentary on this channel, where we covered the same Lidgerwood cableway technology that TVA used. Grand Coulee Dam, which we also documented, was being constructed by the Bureau of Reclamation at the same time TVA was building its system 3,000 miles to the east. And R.G. Letourneau, the inventor and equipment manufacturer we profiled in one of the most watched documentaries on this channel, supplied earth-moving machinery to contractors working across TVA dam sites throughout the program. The numbers that define the TVA construction program are difficult to absorb all at once. Approximately 125,000 people were moved off their land. Over 14,000 graves were excavated and reburied on higher ground. Thousands of workers were injured. Dozens died, though a complete program-wide fatality count has never been published by TVA, and the records remain in federal archives in Atlanta. Families who had lived on the same land since the 1700s watched their homes disappear under rising water. Communities that had existed for generations were erased from the map in a matter of months. The Tennessee Valley today generates about 30,000 megawatts of electricity. TVA remains the largest public power company in the United States, serving 10 million people across 7 states. The dams still stand. The cableways that built them have long since been dismantled and scrapped. The batch plants have been torn down. The construction camps were bulldozed decades ago. The towns they drowned rest at the bottom of reservoirs that millions of Americans now use for fishing and boating and lakeside recreation, often without knowing that beneath their hulls lie the foundations of houses and churches and schools that were standing when their grandparents were born. Occasionally, during severe droughts, the water level drops low enough to expose the old roads and foundations. The stone walls reappear for a few weeks, and then the water rises again and covers them. We spent weeks putting this documentary together, and one of the things that struck us was how little attention the actual machinery has received in the decades since these dams were built. The political story of TVA has been told many times. The social story of displacement and rural electrification has been covered in films and books and academic papers. But almost nobody talks about the cables and the buckets and the batch plants and the operators who ran those systems 400 feet above a river with nothing but friction breaks between them and disaster. That is the story we wanted to tell, and we hope it was worth your time. If this documentary meant something to you, like and subscribe. Every film takes days of research, and we make them because people like you keep watching. We will see you on the next one.